So the third component is visual homing, also known as view-based translation or something to that effect. And this would be translating to move up the familiarity gradient. Eventually, for a complete insect-inspired solution on robotics, we'd use all of these tools in the toolkit, and they enable robustness through redundancy. But for my talk, I'm just going to be focusing on the visual compass. And I'll start by describing the artificial implementation of the visual compass. So during training, the agent traverses a route. On route traversal, it will acquire a panoramic view, and a sort of standard resolution we might use is 120 by 25. So this is about 3,000 pixels. The panoramic view is flattened and input to a neural network, which we train with an Infamax learning rule, and then we discard the view. So we don't need it anymore after training. So it'd be acquire, train, discard, acquire, train, discard, acquire, train, discard, all the way through a route. And just to talk about the Infamax learning rule a little bit more, we use a single layer neural network. So it's just input, weights, output, and it's been demonstrated to do simultaneously independent component analysis and memorization. And the nature of it is anti-Hebbian, so that after training, familiar inputs will result in a depressed response. And we can use that to determine if the view has been seen before, essentially. So during the testing phase, the agent scans, which Andy mentioned, as a sort of innate evolved behavior, and by doing so, orientations of a view are presented to the model. The scanning could potentially be done in silico, and in our implementations that are artificial, it is done in silico. And the output of the scanning is a graph of orientation versus view novelty. And what the agent has to do is turn towards the angle where the novelty is minimal and then go forward. And in this way, it can follow a route. So just to reiterate something Andy was talking about, there's no matching of a current view to a specifically remembered view. There's no mapping to where in the route that's from. All the agent needs to know is whether or not the view is familiar. And so this embodies route following. And I'm just going to show an example of the agent navigating in a simulated Unity world. So the agent was trained on this red route, and it's now in the testing phase. So you can see a typical view in the top right corner. As you can see, it's quite low resolution. And the bottom right corner has the plot of orientation versus view novelty. And at each step, the agent is just turning towards the minimum in the bottom right plot. And in this way, it can follow the route. And you'll see in a second when it goes off route that the plot becomes noisy because there's nothing familiar. So I'm just going to talk a little bit about the environments in which we test navigation. So we do some in the simulation. So we currently use a Unity engine because we can procedurally generate terrain. We can add wind models. We can sort of create agents at sensible dimensions. We also have a lab space, which is populated by these fake trees, and that's just useful because we've got a motion capture sentence so that we can have ground truth of what the robot is doing. We don't use it for the navigation, it's just there so that we have exact ground truth. And we also have a rover that we can take outdoors into the sort of habitats that a wood ant might exist in. And we also use grid worlds just because that makes evaluations much faster. So first, I wanted to look at whether or not Infamax was robust to varying environmental conditions. And as a starting point for evaluating it, we acquire images on a traversal of a route. So drive the robot down a route, acquire the images, and then analyze them offline. So the question that we're asking here is, are the correct orientations recalled after training? If it doesn't work in this instance, it's not going to be suitable for navigation. And what we typically do is divide the image set into odd and even, so that odd might be used for training and even indices would be used for testing. And what we find is that Infamax has consistently good performance across a range of environments with a mean heading deviation from the true orientation of less than 1 degree. There are a set of routes that go up to 14 meters. This is across various environments, so indoors, outdoors, and virtual. But the thing that we've really found is that input standardization is critical. And I just mentioned this because it's not always outlined as an implementation step in the Informatics literature. When you look at the learning rules, weight updates proportional to the pixel intensity. So you have to do this to be using the standard learning rate. Just to look at a bit more in terms of varying environment conditions, we use noise as a bit of a proxy to varying conditions. And we see that Informatics, because it's doing this independent component analysis, when you train and test a route on different noise levels, you can still maintain quite a good mean heading deviation. Whereas if you were just looking at the pixel difference between the images, once you start to add noise, the headings selected start to deviate much quicker. So 14 meters isn't very long, so we try to acquire a longer route, and we use the rover and woods outside of the campus in Brighton, and acquired a 700-meter route with over 8,000 images, and again did the same process of training on odd indices and testing on even ones. And for the 700-meter route, we acquired a less than 1 degree mean heading deviation error. So the algorithm is successful on a real woodland route. We really need to test it on a longer, fully panoramic route until it starts to break down. We want to answer how far can we robustly navigate, and when does Informatics actually break down? And the answer is it depends. So first of all, view size must be selected appropriately. So we acquired a 10-kilometer data set in this procedurally generated simulated woodland at 1 image per meter. And we looked at using different view sizes, view resolutions. So the standard is about 120 by 24. We went larger and smaller. And what we find is that for a fixed route length, navigational quality is better if your image is larger. What to take home from this for me is that if you know your robot is going to navigate in a constrained environment where it doesn't need to do long routes, you can make a compromise for your processing power, your memory, your sensors by using a camera that has a smaller resolution. If you don't need to be navigating for 10 kilometers, for instance. Similarly, view density must also be selected appropriately. So by view density, what I mean is number of images acquired per meter as you're traversing the route. And if you're acquiring the images at a consistent rate, so something like 20 frames per second, for instance, this is analogous to your speed. And what this plot shows is that at a set distance, smaller resolutions, for smaller resolutions, you need more images to maintain the same navigational quality. And I think this is a bit like making up for a lack in spatial resolution by considering the temporal domain. It's a bit like when insects go slower when they're learning, perhaps. And I also wanted to look at the eventual profile failure, what that looks like. So I acquired an even longer route at suboptimal image density just to really make it fail. And we wanted to ask what happens as the route extends. So does it just forget the start, or are all memories corrupted equally? So we see that for this first kilometer route, after training and testing on increasing portions of the route, the behavior does begin to approach random, so it is failing. And the profile of failure, once we've trained on the entire route and tested on segments along the route, is consistent. So it's not like the memories from the beginning of the route are forgotten. Instead, all the memories are corrupted equally. And longer routes can be achieved. It's just that I wanted to see this profile failure, so I made sure that the parameters were suboptimal. So we can see that the visual compass is quite robust for recalling the navigation of long routes in a single network if you pick the right parameters and you standardize as required. But robust navigation isn't just about perfectly retracing the same route. For example, insects demonstrate flexibility in relearning when faced with disruptions that mean that they're still able to navigate between two areas of interest, but they're not necessarily following exactly the same route to do so. And this flexibility allows for rapid and robust navigation. So I'm going to talk about one experiment in particular where that demonstrated ants learn aversive action from visual memories and negative associations. So in this experiment, the ants were trained in a straight line between the feeder and the nest. After some time, an invisible pit was placed between the feeder and the nest. So there are no visual cues of this pit. It's invisible. The ants fall into the pit and are able to escape by traveling to the center of the pit, and where there is a little bridge from which they can escape. And after 24 hours, about half of the ants learned to avoid the pit by going around it. So because the pit is invisible, it suggests that the ants have a memory trace, which they use to perhaps train another network. So the author suggests that there's the presence of an antagonistic network. So there's the appetitive route network, which is that route from the feeder to the nest, and then there's an avoidance or aversive network, which is pushing the ants away when they come across a negative reinforcement. And there is evidence in the mushroom body, which is a memory circuit for visual and olfactory associations that we find in some insects, of these antagonistic networks. And so we carried out a simple experiment using a grid environment of our lab and the motion capture system. We outlined a route from a fictitious nest to a fictitious feeder. And initially, we trained an agent on this route, so it's about 100 images. And during the first repeat, the agent is instructed to follow the route network. However, if it comes across a negative reinforcement, so this would be like falling into the trap, it should train an aversive network with the views from the memory trace. The memory trace consisted of 10 images. During the subsequent repeats, if the familiarity of the aversive network is high, the agent is instructed to take an aversive action, so for instance, a 90-degree turn. Otherwise, it should just continue to follow the route network. If it comes across further negative reinforcement, so it's still falling into the trap, the aversive action did not succeed in avoiding the trap, it should continue to train the aversive network with views from the memory trace. And the termination condition is essentially if the trap was avoided, so if the agent is successful in avoiding the trap. And these are the repeats demonstrated by 50 agents. So during the initial repeat, as expected, they're going in a essentially straight line. But as the repeats continue, you can see this going of the path towards the right, which makes sense because they've been instructed to take an aversive action. And given that the disruption is invisible, there's no other way than to have this sort of iterative process of correcting on each route. There's no way to sort of observe the disruption, determine its dimensions, and then avoid it. So at the end of the repeat, we wondered if, after a successful traversal where the trap was avoided, is the future success rate improved by retraining the route on the last successful recapitulation, or should we just maintain using the antagonistic networks? So should we just keep the straight route network and the aversive network, or should we retrain on this final route, which was successful, and then discard the original route network and the aversive network? And we get better results, so 74% successful detour rate if we keep the antagonistic networks. We still have a 52% successful detour rate if we retrain the route network and discard the original networks. So it seems like it is beneficial to keep going with this antagonistic network method. However, this might be because we're only using one of the tools in the toolkit. We're not looking at path integration. And if we look at the routes that we use to train the final route network, it's got lots of bends in it. And this means that we're training on images that are very similar to each other, but facing different directions. So we're giving the agent conflicting information. So if perhaps we have something like path integration or momentum to maintain straighter portions, or just ensure that we were learning within a similar vector, then perhaps this would be more successful. So in summary, insect-inspired navigational strategies scaffolded on evolved brains, bodies, and behaviors can, with the right parameters, learn a route through a single traversal and robustly recall the orientations required for route recapitulation. There is a limit to how much a single layer network can learn. Not sure if these networks are quite large when it comes to considering capacity of an ant's brain. Perhaps they are, and perhaps that's because, again, we're not considering all the tools in the toolkit, so we're not integrating the other sensory information. And bio-inspired networks, antagonistic networks, might be a component for ensuring rapid and adaptive relearning for robust navigation. And in future work, we're going to look at negative reinforcement delivery on a robot rather than this being artificial, and also look at generic aversion. So ants can also avoid predators, for instance, but that's more of a general view rather than using a specific memory trace to chain an aversive network. Thank you. I'd like to acknowledge my supervisors and colleagues.